To start with, I would like to welcome Claire Marks, the President of the Royal College of Surgeons, who apologize, to come and address us. Claire.
Well, good evening, ladies and gentlemen, and welcome to my humble home. I'm Claire Marks. I'm an orthopaedic surgeon by trade, and I've been president for the Royal College of Surgeons for 2.5 years. And one of the things that distinguishes me from other presidents is that I'm the first woman president of the college in 214 years of it being a Royal Medical College. We're in this lecture room, which actually celebrates the efforts of women in medicine. On the wall, there's a schemat there, which runs back through some of our history, and perhaps it's particularly pertinent that Elizabeth Garrett Anderson, who is the second row down from the back first name, she applied to this college to take the qualifying exams in 1865. In those days, you could either qualify through the apothecary's route or through the colleges, the medical colleges and the surgical colleges. And I'm ashamed to say that the Royal College of Surgeons denied her access to our examinations. And then later, about 30 years later, she became Dean of the Women's Medical School, and she applied to the Royal College of Surgeons to allow her students to take the exams, and she was denied access to the college. And then in 1906, the college had a referendum of its members and fellows, and as we've just experienced, you don't always get the result you think you would like from a referendum. Anyway, sadly, the 15,000 fellows and members of this college voted against allowing women to come into the college. But fortunately, the enlightened council of the Royal College of Surgeons realised that this was not a sensible thing to do, and in 1908 they actually admitted women. And then in 1911, Eleanor Davis Colley became the first woman fellow of this college. So we've had a rather sort of short time, with women only being here for a relatively short period of the years that the college and then the Royal College has been in existence. This building, as you came in through the wonderful portico, 1800 portico. The rest of the building actually is from the 1950s, because sadly the Luftwaffe had a go at it in the wars and comprehensively rearranged everything except the frontal portico and the amazing library above it. And we are just about to actually do a bit of rearranging ourselves, and we are hoping that later on next year we will be moving from this building and squeezing into the second building beside it, whilst we rebuild the back of the building to make it into a much more functional college. So for those of you who are interested in buildings photography, now's your chance to take a few pictures of this. I'm not going to take up any more of your time, just to really welcome you to the Royal College of Surgeons, to say you're all particularly welcome tonight, and I'm delighted that we are to be hosting this medal for you, and I'm very much looking forward to hearing our guest lecture. Thank you very much.
Right. Before we go into the presentation of the medal, I would like to explain what the medal is all about. It was established by the Society in 1958 in collaboration with the Royal College of Surgeons, Royal College of Physicians, and Royal College of Obstetricians and Gynecologists. The first medal was awarded in 1958, and since then the criteria has changed. The criteria now is that the medal is awarded for an outstanding contribution to the advancement and or application of medical photography or wider fields of medical imaging. In fact, this puts the medical photographers at alert, because they have now to compete with images which are produced optically and non-optically of diagnostic nature. Well, it's going to be interesting days to come. And the very first medal was awarded in 1958 to Charles Engel, who was the head of the medical photography at Guy's Hospital. He's now 96, and I had the pleasure of having lunch with him only a few weeks ago. Mr. President of the Royal Photographic Society, you have 2 tasks to perform tonight. And before I do that, allow me to introduce you. Walter Benzie, Honorary FRPS. Although a qualified chartered accountant and a senior partner in his firm, he finds time for the Royal Photographic Society. In fact, he is an accomplished photographer in his own right, having got his distinction of associateship in applied photography. And he has managed as an accountant to keep the finances of the society on track, but then I would say so because my expenses get paid promptly. Walter Benzie, please, would you like to step up? And you have 2 tasks, 1 to present the medal, 2nd to introduce the speaker, please.
Don't forget. And would you like to come up? We're going to have a photograph, are we? Just a very brief introduction of Dr. Iddan. Can I just explain in this august company here that Dr. Iddan is in fact what we would call a PhD. He's an engineer primarily, but working in the medical field. Dr. Iddan is an electro-optical engineer and the inventor of wireless capsule endoscopy. It's a wonderful thing, Wikipedia, isn't it? This was a somewhat, I'll just be very brief and hand over to Dr. Iddan, but this was a somewhat unexpected offshoot of his technical work on guided missile technology whilst working briefly in Boston, Massachusetts, and seeing a colleague suffering from gastro-intestinal. So that was actually the beginnings of the process. So it says in Wikipedia anyway. It's such an interesting story. I'm going to leave it to Dr. Iddan to explain to you. But welcome, sir. Very much wonderful to see you. Flown all the way over to come here with your son. We welcome you, and please come forward here and explain to us exactly what we're going to see in here. Thank you very much indeed.
Thank you. Ladies and gentlemen, it's a great honor for me to be able to present to you today the story of the capsule. I'll try to do my best. The history is not exactly precisely what the Wikipedia says, but never mind. It's a nice story. Let's go with it. The story, the PillCam, it took about 25 years for the PillCam to materialize, and it is part of my 25 years experience in medical instrumentation. I would like first to thank the committee for selecting me, and to Ms. Jo McDonald, who took care of that. And I would like to mention Professor Paul Swain, who worked for many years on the capsule with us, who was one of the inventors, and his work is deeply appreciated, highly appreciated. And now we can move to the story itself. Well, the title that I did choose was From the Notebooks of a Troubled Inventor, because I want to share with you some of the obstacles and how we managed to create a bridge over troubled water and design the capsule. Well, I remember as a child, I was born in 41. It was 2 months after the invasion of Russia, and 2 months before the bombing of Pearl Harbor. So in between, 2 events that actually shaped history. I think so. And I remember as a child, the doctor, I was born in Haifa in Israel, and as a child in a small village near Haifa, the doctor had all his instruments in a little black bag. That's it. That was all what was available. The instruments were very few, the tests were very few, basically urine and blood, imaging was X-ray, and surgery was really rare and complicated. Well, a few devices and instruments were available at that time, and as I said, lab tests were basically based on chemistry and some microscopy, and medication were limited to aspirin, sulfa, who remembers them? They still exist. And there were no basic regulation the way they are today, but the interesting thing is that much of the work done on medical instruments and medicine in general has progressed because of the work of physicians that treated soldiers who were sick and wounded. It contributed a lot to the science of, I think so, medicine and medical instruments. Before the Second World War, the instruments were limited to simple mechanical devices, binocular optics, a little radio and telephone, chemistry, and mobile vehicles. They were the only things that were available after the First World War. But the whole thing, the whole scene changed once the entered the Second World War and the Cold War. Military research expanded and went wild. And funds were available at research institutes, university, anywhere, and there was no sparing on expenses. And so new technologies were invented, and as you can see here, from plain, if it works, it should. Yes, it works. Okay, from plain radio, we moved to integrated circuits. And in general, we can generalize it in the Magnificent Seven that were invented during that period. One is miniaturization, which enabled us to actually shrink the size of devices. Second thing was advanced materials, like all kinds of titanium alloys and ceramics that are the basic today of, for instance, total hip replacement. System and interdisciplinary engineering evolved, regulation and standards were made mandatory. Computer-assisted design and manufacturing enabled the lowering the cost of devices, and computer-assisted management helped to actually archive all the data. And the last thing is robotics. In addition and concurrently, the quantitative aspects of medicine and life science in general were actually turning in from an experimental science to quantitative science, and the quantitative science enabled us to actually introduce all kinds of engineering techniques into designing of medical instruments. And the deep understanding of molecular biology helped us to design, say, lab-on-chip devices that are beginning to be very common today. It led to our experience to use all the engineering approach to design of medical instruments. Now the technology plus the new life science enable actually produce the what we have today, the medical imaging, incorporating, for instance, CT, MRI, ultrasound, and OCT, which is my latest interest personally, optical coherence tomography. And biochemistry, lab on chip, miniaturization-enabled laparoscopy, PCR, and defibrillators. And material, as I said before, enabled the total hip replacement and similar things. And robotics, the Da Vinci, for example, and tissue engineering. They all are the results of the efforts and the funds that were available during the Second World War and during the Cold War. The list of these things grows daily. So, once we know all that, one decides to become an inventor, and he wants to start up an enterprise. Good luck. You need a lot of it. Or, as Louis Pasteur said, luck favors the prepared mind, which I think we should always keep in mind. Well, the first thing that one should do is to start with true medical market need. Never start with technology. Big mistake. First, find a true market need, and then try to fit the proper technology to the market need. Examine many options. Don't try to grab the first thing that appears to you. And avoid NIH, and in NIH I mean not invented here. Many people are trying to stick to what they have in mind, and sometimes the neighbor has a better idea. So try to take it. Check carefully the IP, the intellectual property, patents, because if you don't, you'll find out later on that somebody was ahead of you and you lost the race. Be financially conservative, because the burning rate is always too high. And but don't overdo it, because or else you'll simply freeze the project. I want to sum it up in a little triangle that I usually bring up, and the triangle says this: when you start a project, I'm sorry, I'm going back. When you start a project, the technology is here, but the specification are here. There's a gap between what you have today in the market and what the technology, what the specs are calling for on that new project of yours. So what do? Are you going to wait for the technology to mature before you go on with the project? Is it responsible to continue the project even though some aspect of the specifications are not fulfilled? Well, I claim that knowledge is not only to know what is today in the market. Knowledge is also to know what's cooking up in laboratories, in institutes. In other words, what will appear in the market within 2-3 years. And you have to you have to take it into account, and don't be afraid to continue with your design, with your project, knowing that the technology will match up with your requirements, and they'll meet within 2-3 years. And then, when you're there, you create a triangle, and the triangle indicates that the technical gap has been actually zeroed, and then you have a competitive edge on your competition, because you'll be first in the market. In other words, I want to sum it up and say that true know-how requires information on what's cooking in the lab and by other companies, not only what is available today in the marketplace. And you have to take into account the area of the triangle is proportional to the R&D expenses, R&D cost of the project. So always watch for disruptive technology, because if you don't, you may be surprised and lose your project. And I have many examples for that. They are all summed up in a book called Seeing What's Next by Christensen and Roth, published in 2004. I divide the inventions into two categories. One is a revolution, and the other one is evolution. Revolution is what you see here, that the horse and buggy turn into an automobile by the invention of the internal combustion engine. But then, a new model of a car is not a revolution, it's just an evolution. And so you should always try to stick to revolutions. Your project has to revolutionize the market, or else you are lagging behind. For examples for evolution is the telecommunication. The change in models of telephones is not a revolution, it's just an evolution. But once the telephony moved to cellular and then to smartphone, this is a revolution. It changes the way we live today. And one should aspire to design the project to be as much as possible a revolution. I now want to move to the story of the capsule as an example. Well, endoscopic video pill. I was talking with a gastroenterologist friend named Professor Ethan Scapa, and he told me about this, that was in '81, and he told me about the shortcomings of the endoscopes that were at this time in the market. And he enticed me to find a solution and to the shortcomings of the existing endoscope. He also said that colonoscopy compliance is very low because of the uncomfortable situation. It's only about 50% in the US, about 20% in Europe, and about 10% in Japan. So the market needs something that will help push forward colonoscopy. And he tried to explain to me that the endoscopy, conventional endoscopy, is fine to examine, for examining the upper gastrointestinal tract, and colonoscopy is fine in examining the lower part of the gastro tract, but the small bowel is an uncharted territory. And if you're so smart, he told me, find a solution. Well, I told him, well, it's going to take a few weeks' time to find a solution. Well, it didn't. I searched the literature and learned that the fiber bundle that was used for the first endoscope and colonoscope was replaced by a small CCD camera that was placed on the tip of the endoscopic device. And but this didn't solve the problem of penetrating the small bowel. That was '91. But then I thought about it and I told him, what if we design the device, the endoscope, in a way that the camera will be tethered, will be able to separate the camera from the endoscope. Once you put in the endoscope, separate the camera head, the endoscope head with the camera, and tether it and let it progress into the small bowel. And but he told me, but you're talking about 6 meters. How are you going to pull it out? No way. And what do you think? I'm going to wait for 2 hours for the camera to pass through the small bowel and watch the images? No way. That's not a solution. Try harder. Okay, at that time, the technology was, the camera technology was kind of limited. Same was radio technology. And I couldn't find a good way of doing it. I thought about cutting off the the camera head and putting a small transmitter into it to transmit the images instead of passing them through a tethered wire, but I couldn't find a proper transmitter, so small. And where is the power going to come to the camera? I consulted with some video experts, and they told me that the conventional CCD, if I operate it on batteries, on small batteries, will last probably 2 minutes, and then it will run off power. So no solution. Problem. But then, 1992, 3 new technologies, the annus mirabilis for new technologies in gastroenterology. 3 technologies matured. One was the invention of the CMOS camera on a chip. A single chip was a complete camera. You don't need any extra. It produces a video image, and it consumes only 1% of the power of conventional CCDs, the older generation chips. The second invention was the Asic Transmitter. Again, a transmitter on a chip. It consumed a low power, it was small in size, just 5 by 5 millimeters, and it could actually transmit the video images to a receiver mounted on the belt of the patient. And the last but not least was the LED illumination, the white LED that could illuminate inside, because inside there's actually darkness, and could illuminate the images, and at very low heat, producing very low heat and consume very little power. Well, I felt that now we are in business. During the year of work, I always documented my thoughts and personal thinking in notebooks. I accumulated, I guess, about 40 of them. And I always kept going back, trying to find out what are problems that I actually stopped working on because the technology was not there. Once the technology popped out, I was able to go back to my notebook and restart working on a project that was delayed. Here are a few examples. This is what I wrote in '92, all kind of thought that I have about the capsule, all kinds of designs, but I wasn't happy with them. Finally, in 1993, I have here a sketch of the capsule the way it is now. It has a dome, a transparent dome, a lens, a CMOS. You see that the LED illumination, and that's how I estimated what the image will look like. Here. I assume that the image is going to look like this, and if there is some kind of a lesion or a tumor, you're going to see it in the image. The first experiment, I wanted to know whether we can transmit the video images through the human tissue, biological tissue. The first thing that was available to us was a chicken that was bought in the supermarket, and we placed a transmitter into the chicken and tried to capture the images outside, and it worked. And I documented it, and we found out how much power is required, what kind of wavelength will be optimal for transmitting the images. So you see, the idea of the capsule was 20 years old at the time that we started to work on that. And the joke actually turned into reality. And here are some of the first experiments that we made in building the capsule. And I guess at that time, Professor Swain was building similar things. Weren't you? And the experiment went well, and here is a timetable that actually indicates the transition from actually rigid endoscopy of the 60s through the flexible endoscopy of the 80s, and then finally to the capsule endoscopy in 2000. Well, a new startup requires funds. So actually, a new company was established to finance the device. And at the beginning, I wasn't able to raise money for that. But finally, RDC was, it was a venture capital company who was established, and they agreed to finance the device, to give us the initial funds. And Gavriel Iddan was hired to be the CEO and funded Given Imaging. Now, Given Imaging stands for Gastro-Intestinal Video Endoscopy. These are the initials. Okay. And Professor Paul Swain from London, who worked on a similar concept, joined the team. And we actually transformed the world of GI capsule from science fiction or from joke to reality. Now here is a cross-section, a schematic cross-section of the capsule. As you see, the front side is a transparent dome, and here you have a lens, and the CMOS imager is here. Two LEDs are around, and here you have the batteries and transmitter and the antenna. And the interesting thing is, one of the problems that we encountered during the development was that we had parasitic reflections from the LEDs directly from the dome into the camera, and it actually completely saturated the camera. So we had to design a special dome that was a special dome with a special curvature that didn't let any ray return from the dome to the camera. Or else you saturate the camera and you see only white image. A better cut of the, a better cross-section of the camera can be seen here. And what you see here is the dome. Then you see here a lens holder, plastic lens holder, the lens itself, and then a small PCB that has 4 LEDs. And then comes the PCB that holds the imager. And then we have the batteries, the transmitter, and the antenna, or what you call aerial in this country.
Exactly.
Am I right?
Yes.
Okay, so I have to mention the name of the person who invented the CMOS imager. He was at JPL in California. His name is Eric Fossum. And he later on established a company that started manufacturing these little things. And when we approached him, he was just beginning to manufacture these CMOS images, and we asked him to manufacture for us the device, so small, and we told him this is going to be a disposable device. We're going to throw it each time. And he told us, go away, you're not serious. Go away. I can't do that. And we were really in problem. But then he called us to the hotel, to our hotel, called us and told us that since his father died of undiscovered gastric cancer, for his memory, to commemorate him, he will build for us the CMOS imager. And he did, and it worked. Actually, the device is built of 3 sections. One is the capsule itself. As you can see, we called it in the past M2A, and now it's called the PillCam. The second part is the recorder that is attached to the belt of the patient. And finally, we have the workstation where the physician is actually reading the images and making the diagnostic. And Here are some typical images, old images, taken with the camera, with the first model. They were fairly poor, but they actually indicated all kinds of problems could be indicated by the through the images and discovered through the images. Here are some more images. And okay, here's the timeline. As I said, in 1981, I met Professor Scappa, and he told me about the need for something for the small bowel. Only in 1992-93, all the technology matured, and we were able to design a capsule, and we applied for a patent. And we did the experiments on the chicken. And the FDA was granted at 2001, and the first capsule was sold in the market at 2002. So it took more than 20 years of work from the very beginning to the first capsule sold in the market. And that's the way we looked, Professor Scappa and myself, when we started work, 81. And this is during, and this is right now when we enjoy our grandchildren. So it's quite a time. Right now, the gastric capsule is not a single capsule anymore. It's a family of capsules. We have a capsule for the esophagus, we have the conventional capsule for the small bowel, and we have the colon capsule. And the current status of the capsule is this. We manufactured already about 3 million capsules were actually sold and swallowed. The resolution improved from 65,000 pixels per image to 120,000 images pixels per image. And the viewing time, which is a very important factor, was reduced from more than 45 minutes per session to less than 10 minutes. In other words, the physician today can sit near the workstation for just 10 minutes and diagnose the patient. And we have the esophagus capsule, which has 2 viewing heads and is used actually with 60 frames per second. So it's a full video. The older capsule used 2 frames per second, and they were then changed with the software into a continuous video rate film. I want to show you some samples that I have here. So this here is a 2-sided capsule that actually blinks at 2 frames per second. And you can reverse it around. And then there is one that is an exploded view. You can see the parts. And I have a few mock-ups that you can actually help yourself and take, but don't swallow them. And don't let little children swallow them. Okay. This is the newer model, and you see that the images have improved tremendously, and it's fairly easy now to identify all kinds of problems in the gastric tract. You can see very easily, here bleeding. You can see here all kinds of polyps. This is the transverse portion of the colon. Another polyp. And Professor Swain can explain it better than I do. Here still some more images, and here I think I did give some sizes to them. This is IBD, irritable bowel disease. And here you can see all kinds of Crohn's, bleeding, another polyp, and severe ulcers and erythema. Here one can see a 20 millimeter bleeding polyp, 20 millimeter bleeding polyp, 11 millimeter polyp, 9 millimeter polyp, a tumor, an ulcer, and tumor stenosis. There are new US indications now for Crohn's. The capsule is approved for use in Crohn's. For patients that have elevated risk, replacement for colonoscopy. The new software version, the Rapid 9, was released, and new images are now accumulated into an image bank, sort of an atlas that one can use. Now, what is the future of the video capsule? This is my own prediction. Nobody else is responsible for that. The resolution is going to increase to 1 megapixels per frame, and you'll be able to observe 20 micron objects in the image. There will be an adaptive frame rate. Frame rate will change according if the capsule is actually stationary for a few minutes. Why waste electricity? You don't have to spend electricity and take more photographs. You stop taking photographs, and when it moves again, it has a small motion sensor inside, and it will actually activate the capsule whenever motion is indicated. Image processing will assist the physician in pointing directly to lesions, which will help a lot. And OCT capabilities, as I said, OCT is optical coherence tomography, which is an infrared ray that can penetrate into the tissue, and it will enable submucosal observation of whatever lesion is seen. And there will be multispectral imaging, which also helps the physician to identify the problem. And lab-of-chip capability will enable to do some kind of biochemical analysis on board the capsule. But this is my own prediction. The product line expanded, and as you can see, imagination has no limits. And so, having told the capsule story, I want to return to some more general observation regarding the future of medical R&D. It's going to be problematic, but there is some hope to it. As you know, classical economy say that invisible hand and division of labor will solve everything, by Adam Smith. And then we had Keynes' corrections post-World War I that say that government intervention and regulation will do the job. But nowadays, things have changed, and as some people say, the rules have changed, and we have to now take into account the environment, outsourcing, regulations, and things have changed, and when we try a new project, we are facing now tremendous difficulties. The new era and the rules have changed. So the old traditional industries had to close, rest in peace. Traditional heavy industry, textile industry, and consumer products gone overseas. In some cases, management sensed the changes and entered new fields like Microsoft, Intel, Facebook, cyber, green tech, biotech, and medical devices, where we are concerned. The factor that will be affecting the new designs in medical industry are tough safety regulation. The FDA is very tough and very expensive to come by. High cost of medical care, the low cost of manufacturing overseas affects the product design, and tough environmental laws. Investors intervene in the company's operation. There are sometimes pain in the neck, to say the least. Patents are consuming funds, and computer communication, embedded computation, and IoT are going to affect future products. So, how should we take care of that? How should we operate under these changing rules? What I have in mind is innovation and quality. Innovation and quality is going to save us. How can we do that? Well, first of all, we have interdisciplinary education, because today's designs have to be interdisciplinary. They are not associated with one single field of learning. You have to combine at least 2, 3, 4 fields of learning to produce a new product. And do not be afraid in case of failure. There are some places where people are afraid to dare and make big jumps because they're afraid that they'll fail and lose face. That's not the case anymore. You can't afford it. Mind the alternatives and be responsible, mind the expenses. As we said, the cash flow is always problematic. Do not give up when in trouble. Well, we visited today the Churchill's underground headquarters, and we noticed how a person was able to, even if the times were very difficult, he never gave up. There are some positive indicators that are going to help us. The government seed funds are great for startups. They exist today. And demand for new techniques and high-tech products, medical products, is on the rise. And we have rapid technological progress is providing us with new capabilities. New devices are available, new technologies. Going beyond the imaging capsule, the program already underway for the next generation, which will include maneuvering capabilities, basically magnetic maneuvering of the capsule. So we'll be able to steer the capsule inside the body and not solely rely on peristaltics. Molecular diagnosis on the chip. Other potential applications including drug delivery and virtual biopsy. First human trials are already in progress. We did some experiments with movable maneuvering the capsule, and it seems to work. It's going to take a lot of efforts to finish it. I want to say a few words about resolution of images. I think that one day we'll be able to analyze on the spot, on the point of care, to analyze the resolution will go below 10 micron, and we'll be able to see actually cells, or even inside the cells. We may be able to do some on-the-spot diagnostics, or even identify tumors and the lesions, but it requires actually resolution much better than we have today. Okay. There are some hot topics that are now progressing, and then one is point-of-care real-time diagnostics. As I said, the optical biopsy, minimal invasive treatment. By maneuvering the capsule, we'll be able to do all kinds of other things that we don't do today. Genetic profiling, brain research, and tissue engineering. These are the leading directions which we try to work for. So, to conclude, we start with market need and not with technology. We are not afraid to anticipate new direction in technology, and we incorporate them in our design and into emerging technologies. We get the best people and advisor, no matter where they are or how much they cost. It will pay. And the innovation is absolutely critical to companies, nation, and society. In other words, revolutions and not evolutions. We should have patience. It may take a long time. Things that seem impossible today may be evident tomorrow. And do not be afraid to fail sometimes. And I guess that's about it, and I thank you for listening.
Dr. Iddan has kindly agreed to take questions and any comments. I'll take questions if you put your hands up in turn. Yes.
Well, thank you very much for your talk. It's a fascinating subject area. 4 years is a fantastic time for an FDA approval. What challenges did you find in that time that were the hardest to overcome?
The problem is that most investors, the venture capitals, they are expecting you to give them return on investment within 2, 3, maximum 4 years. And unfortunately, in medical devices, that's very difficult to achieve. When you design a new application for your smartphone, you can within a year or two finish the project and return the investment to the investors. But that can't be done with medical instruments, and we have troubles. That's the reason why I emphasize the fact that the governments have to support the development of new medical technologies. Because private investors will agree to pour money only after you show some success, after it works. Well, that's no big deal.
Dr. Iddan, one important thing perhaps you did not mention, by the time the patient swallows the pill, it should be defecated or excreted by next day. If it doesn't arrive, you panic. Now, if it doesn't arrive after 3 days, then it's got to be found. Now, is this done by keyhole surgery, and how is it identified exactly where it is?
I can record only one case where a capsule was retrieved after 3 years. It was in Australia, I think. Yeah. Long way and long time. And what we have now is a special capsule called a Patency Capsule, which is a capsule that is used only to make sure that the passage is clear. And if it gets stuck in a certain position, it will melt, it will actually dissolve and disappear. And so it will tell you if there is a danger, if that patient is not a candidate for swallowing the true capsule.
Right. Yes, Bob.
Designing a product which is going to be ingested by a patient, did you have a lot of difficulty in developing materials which would be inert and wouldn't damage the patient as it was passing through, poison them or whatever? Did you have to take special precautions with the housing, if you like?
We had to be very cautious about it, but the materials already existed. They were used in all kinds of medical instruments. There were all kinds of polymers, plastics, and of course metals that were okay, that were used and were okayed by the FDA. So we didn't actually have a severe problem with materials.
Thank you.
Tony?
You said earlier we can call you Gavriel, so Gavriel, thank you very much indeed. If I got your talk correctly, you mentioned the concept of multispectral imaging, and if that's going to get incorporated into a PillCam, my questions are, what range of wavelengths would you be looking at, or what would you be using as light sources for multispectral imaging? You said earlier we can call you Gabby, so Gabby, thank you very much indeed. And if I got your talk correctly, you mentioned the concept of multispectral imaging, and if that's going to get incorporated into a PillCam, my questions are, what range of wavelengths would you be looking at, and what would you be using as light sources for multispectral imaging?
Okay. I assume that the range will be between, the range is going to be between 0.5 micron or 0.4 micron and 1.7 micron, not beyond that. That's the range, which is the lower range of the infrared.
One other thing, Dr. Iddan, you mentioned is tumor stenosis. Now, tumor stenosis narrowing could obstruct the travel of the capsule.
Right.
Is that correct?
Of course it is.
So it will not travel until it's discreted.
It will not travel. You have, if there is a danger of that, of narrowing of the passage, then you have to have, first of all, a patency capsule taken to make sure that it will pass through. And only later you can swallow the real capsule.
Yes. Lady first.
Oh. Well, you mentioned that one of the hot topics was brain research, and I was wondering what
I didn't hear you.
Sorry, you mentioned one of the hot topics for the future was brain research?
Brain research.
Brain research,
Sorry.
indeed. Yes.
I was wondering if you had any inkling of how that would take shape, or any specifics.
I'm not associated with that kind of research, so I can only speculate, and I'd rather not.
All right, I'll look on Wikipedia then.
Any more questions? Yes?
Thank you for a very interesting talk. This was really nice to see the whole history behind developing capsule endoscopy. My question would be your personal opinion on the future regarding, you mentioned at the beginning of your presentations that typically to image the gastrointestinal tract, it would either be a matter of using a flexible endoscope, or in order to close the gap in the small bowel would be the use of a capsule system. Do you foresee, and I guess both systems have advantages and disadvantages, do you foresee in the future an amalgamation of these two techniques, a hybrid kind of an approach? And if yes, what would that look like?
For example, I can see that the endoscope has a capsule at its tip, and you make the examination and conventional endoscopy, and at the end of the endoscopy, you simply let the capsule loose to continue the small bowel. That's a possibility. There is another problem that was raised at the beginning. You know, when I started the project, everybody was telling me that no chance. There are 10 reasons why not to do. First of all, the window will get dirty in a minute and you won't see any images. You don't have windshield wipers. The other thing, nobody needs it because there's nothing in the small bowel. The other thing is that probably somebody did it before, and there are 10 reasons why not to do. And one has to analyze these reasons very carefully and see whether they are true or false. And in the case of the capsule, I was convinced that it is a false statement, that there are 10 reasons why not to do the capsule.
Yes, Hussein.
I wanted to ask you, during the course of the journey of the actual capsule, would there be any need for the patient maybe to undergo, for argument's sake, MRI or any radiological examination And what would be the effect of
Usually,
the actual capsule in terms of magnetic resonance?
Usually, to the best of my knowledge, you don't take MRI if you have some metallic bodies, metallic device attached to the body. So I don't think that the person that swallowed the capsule will be able to go through a MRI. I think so. I think it's not possible. And the time that it takes will be usually, once you swallow it, well, I say that for one person it took 3 years, but usually it will take, before it excreted, will be about 2-3 days maximum. And you can actually enhance it by taking all kinds of helping. We have a whole book of jokes about the capsule. And you can imagine somebody said that it's a better business to sell that book than sell the capsule.
See, one other thing would be interesting. Not everybody in the morning when they sit down are looking for it. Could this device have a sort of a warning system whereby it bleeps so you know it's come out?
I think we are penetrating the area of the...
It would be a good idea to say it bleeps
Yeah,
so you know
well,
it has come out.
You know that in Japan you're not allowed to simply get it out into the toilet, so we have to sell it with a special kit, capturing kit.
A capturing kit.
You want me to continue?
Yes.
I just wanted to know, I know you mentioned you tested it on a chicken. I've just seen, what other research did you undertake with patients? Did it
I
go through?
couldn't hear.
Sorry, could you just repeat the question a bit louder, please?
What was the patient research aspect?
You did it on the chicken first, but what patient research did you do?
The first patient sits here amongst you, the audience. It's Professor Paul Swain, who was the first person in the world to swallow a true capsule. I swallowed a few inert capsules ahead of that without an imaging device, just to measure the time, to do the timing. I swallowed about 12 capsules.
Not at the same time.
No. No. And some other people did also swallow capsules, but the first true imaging capsule was swallowed by Professor Swain.
Was it comfortable?
It was entirely comfortable. I've had lots of endoscopies because I'm a professor of endoscopy, and they're all uncomfortable, but when I swallowed the capsule, that was completely painless. It's a slightly large thing to swallow, so it's a slight surprise, but once it's gone down, you just don't know it's there.
The idea is that when a person needs that examination, he comes to the clinic in the morning, he swallows the capsule and gets the belt with the recorder, puts it on, puts on his jacket and goes to work. And at the evening, when he comes back from work, he stops at the clinic, returns the recorder, and that's it. And the physician later on sits in front of the workstation with a cup of coffee and looks at the images and decides what to do.
Dr. Iddan, I have two questions. One is, the subject matter being photographed is in very close proximity,
Yes.
which would mean your lens is a wide-angle lens to give you depth of field.
Yes.
So what focal length is the lens?
The focal length is, to my recollection, is about 3 millimeters?
2 millimeters.
3 millimeters.
3 millimeters.
Yeah, to the best of my recollection. And the pupil is so small that you can get to that nice depth. It's almost a camera obscura, almost.
Does it make a difference which direction the camera is facing as it goes down? Does it looking backwards would be just as well as looking forwards?
It makes no difference. Professor Swain, can you say a few words about that?
I think that's true. We do actually have some capsules which Professor Iddan has shown you with two images, so one that looks backwards and one that looks forwards. In fact, probably only in the esophagus it sort of matters because it passes under gravity and gets through the esophagus in about a second, and so it's helpful to have images both ways if you want to look at the lower end of the esophagus. But it probably doesn't matter, and in fact we don't really know which way it's pointing when we're looking at the images afterwards. You can also see the gut squeeze down, it propels it forwards, but sometimes it propels it backwards as well. You can see it squeeze down and propel it.
Well, that being the case, then there is a possibility you could have 3D imaging as well.
Theoretically, you can, because if you have a series of images, you can generate a 3D image out of a sequence of 2D images. There is such a possibility, but nobody was really interested in that up till now. If the requirement will surface, then we may as well do something
Well,
about
the
it.
reason I'm mentioning it because it would be useful to be able to measure the size of the regions.
Oh, you can do it right now, today,
Okay.
even today, with the existing technology. You do it. They do it. And I actually stated, gave a few examples of 9 millimeters and 12 millimeters and 20 millimeters.
Girish?
With the normal endoscopy and colonoscopy, the patient has to have a preparation, and that's one of the worst parts. But with this thing, do they need to prepare things, and can they eat anything normally afterwards? Once the pill is inside?
To image the SB, you don't need to have any special cleaning. You just have to refrain for a few hours from eating, that's it. And then you can swallow the capsule and the small bowel will be clean. That was one of the big surprises, wasn't it? That
Certainly was. I mean, basically the stomach takes about 40 minutes to empty. If you eat while in that 40 minutes, the image just disappears in the food. So you need, the small bowel is almost completely empty most of the time, and so you don't really need cleaning. Some people like to clean it because it's slightly better in some cases. The colon is always a problem and does need full preparation, like for a colonoscopy.
Yes?
Which countries is this available in as a diagnostic tool?
which almost all over the world. You can get it here in London, definitely.
Can you tell us something about the cost?
Yeah, the cost of the capsule was about $500 US dollars per capsule.
Down the drain next day.
As they say, tough luck.
Michael.
Is it something that you can give to children or babies, or is it purely for adult use?
The youngest patient that I know of was a 3-year-old boy from Norway that swallowed the capsule. He didn't swallow it, he had to be anesthetized, and it was pushed into his gastric tract, and it actually found a bleeding in his small bowel, and that was repaired by minimal surgery. And they sent us a picture of him playing with his friends football, after 2 weeks or 3 weeks after the operation. And that boy suffered from bleeding since he was born, and nobody knew where exactly the problem is.
Is the capsule size an optimum size now from a medical point of view, or would it be better, is it always trying to get smaller and smaller and smaller?
It's a good question. The technology now exists, we could actually make it smaller. But I'm not sure it's going to help, because the size of the capsule now fits well the small bowel, and it sits good, and if the capsule would have been smaller, it may do all kinds of wiggling, which we don't want to.
Yes? If I may have another question. With the advent of near-field communication and low-powered Bluetooth, is there any incentive to incorporate the capsule endoscopy with a smartphone?
Yeah, it is possible. Once you capture the images, you can actually send them to a specialist by ways of smartphone. If the physician wants to consult another physician, he can send him the images.
But I mean acquiring the actual data and localizing the pill at the time. Is that been something that's been considered?
I don't think they work on that right now. There was no market interest in that.
Thank you.
Any more questions or comments?
You said it was for single use, and I can probably guess why that might be, but I wondered whether there's ways that in perhaps some of the less developed countries of the world, perhaps in Africa, there's ways to have it reusable so you can actually get more value and benefit for local populations that might not be able to afford that $500. Has any thought been given to that?
There are some problems in that. Say that you somehow retrieve the capsule and you wanted to reuse it, then you have first of all to take it apart and replace the batteries and then seal it again and test it, and finally you end up with the same cost as a new one.
Jeff, does your current production meet clinical needs? You talk about volume. Are you able to meet the demand of
the annual rate of manufacturing right now is 300,000 per year, and it seems to be okay. It's increasing slowly. It will probably flatten. The demand will flatten at 500,000 per year.
Okay, any more question, any more, sorry, Henry, yes?
I was just curious, during the process where you were designing, like really in initial stages, did you have any competition from other research groups?
Okay, we had later on, the good thing is that once a project seems to be, or an idea seems to be successful, then all of a sudden you get all kinds of patent claims and from other people, and that's a good indication. It means that it's worth. And we had a few of these, and we had to go to courts, especially in the United States. And our biggest competitor was a small minor company called Olympus from Japan. But finally, we came to terms with them, and we still hold about 95% of the market, and they have about less than 5% of the market. And they are permitted to manufacture capsules, and we are permitted to use their patents. That was the agreement. And they paid a certain amount, and the case was closed. But I have to tell you an interesting story. I was involved in another project, and during that project I had to go to the US to a venture, talk to a venture fund, and I was there introduced as the inventor of the capsule, and then the manager of that venture fund started laughing. So somebody asked him, "Why do you laugh?" He said, "That's about 100. I heard about 100 people that invented the capsule. You are the number 100." So.
Right, okay, it seems you have answered all the questions, and there are no comments. That remains me to thank you. Before I do that, let me assure you that your talk tonight was educational, informative, and entertaining.
Thank you.
Now, you expressed your interest, your new interest in OCT.
Yes.
Now, you should have been here last year when we had Professor First Year, one of the pioneering person.
From Vienna.
Yes.
I heard
He
about
was
it.
the winner of the recipient of the medal last year. And he showed us very simple diagrams, simplified so easily that we understood everything he told us.
So you don't need another lecture on OCT.
Well, we need somebody to decipher what he told us. So thank you very much for that talk, and we wish you well. And although a bit early, Merry Christmas to you and to your family.
Thank you
Safe
very much.
journey. And we admire the patience of your son sitting there. I don't know how many times you heard your father again and again, but
Well,
thank you for being with us.
He is basically interested in ancient metals.
Ancient metal, yes, I remember.
Ancient metallurgy. Yeah.
So thank you very much indeed for
Thank
that.
you.
Before we close the meeting, may I remind you that the nominations for this medal are now open and is available on the RPS website. The address is www.rps.org. And I think the nomination is up to 16th of January for 2017 recipient. We will have another speaker next year who has been awarded the same medal. The date is to be announced. Am I right, Joe?
Oh, what, of the next lecture?
Yeah.
I haven't actually thought
Right,
about
okay.
it yet.
This is too early. All that remains for me is to say a few thank yous. I would like to thank the Royal College of Surgeons. Thank you very much, Mr. Marks, for being with us, and thank you for hosting us. Thank you for your hospitality, and would you please convey the same to your colleagues. I would also like to thank the other Royal Colleges of Physician Obstetricians who are partners in this medal for their continued support. Walter, thank you very much. I know you're a busy accountant, busy president. Thank you for finding time to be with us. I would also like to thank the Chief Executive, Dr. Michael Pritchard, for being here and doing the logistics behind the whole thing. And I would also like to thank Science Photo Library, who have kindly sponsored the video recording tonight. So thank you, Anton. I would like to thank Judith Mitchell. And last but not least, the person who put the whole thing together, which is involving a lot of logistics, is Joe McDonald. Please give her a very big hand. May I wish you a safe journey home, and although a bit early, Merry Christmas to you. Good night.